Well, we've got a great treat today. I've got one of my colleagues from our Geology and Geophysics department, Professor Kanani Lee. Kanani is an experimental geophysicist. She did her undergraduate degree in physics at the University of San Francisco and her PhD at Berkeley. She went on and did a postdoc at Caltech, was at New Mexico State for a little while, and has been on the Yale faculty since 2008, and does all sorts of cool stuff, right? So, so if you guys, do well, right, get yourselves admitted to Yale, you might be able to work in Kanani's lab or work in one of the field labs in G&G. They just do all sorts of neat physics and chemistry and geology also, right? So join me in welcoming Professor Kanani Lee.
Hi, guys. Can you hear me? No, can't hear me. Let's see. Can you hear me now? Okay, good. Can you hear me now? Right. So I was told that I should give you a brief little, how did I get into science? So you heard my bio, right? I was a physics undergrad. I did my PhD in geophysics, and then about almost 10 years ago, I came here. But why did I come here? Or how did I get here? And so I just want to give you a little bit more of a background. I was actually born and raised in Hawaii. And so for those of you who know Hawaii, you might say, well, gosh, it's pretty obvious then why you went into geology. After all, you live on a volcanic island in the middle of the ocean. And I would love to say that that's absolutely the truth and why I turned into became a geologist. But it's actually not. I studied physics as an undergrad. And at a very young age, I wanted to be a physicist. Now, I didn't know what that actually meant. For those of you who are in the audience who are old enough to remember the television program MacGyver, does anybody remember that TV program? So it was on when I was a kid, and I would watch it with my dad, and I thought, man, this guy MacGyver, he is amazing. What a smart person this person is. So the background is this MacGyver character could basically get himself out of any trouble or with basically a Swiss Army knife and some duct tape. Of course, it was a television show, and so it was very Hollywood. But I was taken by it, and I asked my dad. I said, "So how does MacGyver become so smart?" He says, "Oh well, you got to take physics." And so I was sold, and so I took physics. Turns out physics and chemistry, all of these things are very important in earth science and learning about the earth. And so I took my physics background and I decided to apply it to the earth. After all, this is where we live. And there's so many fascinating things that we observe, that we are part of, that I didn't understand at the time. And there's still a lot of things that we as earth scientists are still trying to figure out. And so this is it's an exciting way to get your science in and learn about what's going on inside the planet. And so in my research, I'm an experimentalist. And so what I do is I try to recreate the conditions inside of our planet and other planets. Okay? And so a little later on during this talk, I'll show you the kind of tools that we use and tell you a little bit about it. But first, let's figure out what's going on inside of the Earth. Okay? So that's the theme of today's little talk here is we're going to try to figure out the Earth from the inside out. Because what I try to do is recreate the conditions inside the planet, and let's see if we can learn anything about what is going on the outside. I also want to make a plug. So before you guys leave today, my family is here. So my husband and my two boys are sitting up on the top row there. And so my husband and I actually wrote a couple of comic books on earth science. Okay, so before you leave today, please grab a copy, take it home with you. You can learn more about it. One is on plate tectonics, which we'll learn a a lot about today. And the other one is talks about the moon. So take that in. They were actually funded by the National Science Foundation as part of a larger grant that I put together. And they were made specifically to be used in the middle schools here in New Haven. And so it uses the rubrics of what is taught in the 7th and 8th grade here in New Haven. So it's geared towards that. But I've had they've been out for a few years now. I've had children as young as my own up to college students use it. So it is meant for everyone. Okay. So the big question, there are lots of questions, but the big question, the overarching question that I try to answer with my research is this, right? How does the Earth work and how has it evolved? And work here is really, I mean, we could use it in many different ways, but how does it do what it's doing, right? So here's what the inside of the Earth, here's what we think it basically looks like. Okay? And we have to infer what it looks like based on what we see on the outside. Okay? And then also some things that we can do in the lab on the inside. Okay. So what are some observations that we see here on Earth? Anybody want to garner some guesses? Yeah. We see volcanoes, right, in the back. Yeah. We see plants and animals. We see life, including our own. Yeah. Buildings. We see, what are those buildings made out of?
Rocks and things like that.
Rocks, that's right, yeah. Cement, right? Natural resources. Like what kind of natural resources? Water, lots of water, yeah. Very, very important. I actually teach a lecture here on campus all about water, but we won't go much into that today. Trenches and mountains, is that what you said? Oh yeah, trenches, good. Yes. Earthquakes. All right, so the first answer of the day was volcanoes. The last answer of the day was earthquakes. Perfect. So you said everything, the two things that I was mainly looking for. But the other things that we've talked about are very important, right? As far as we know, at least in our own solar system, right, life is obviously here on Earth. But the complexity of life is not found anywhere else in our solar system. We're looking, okay, but it's quite unique, and there are lots of reasons why that is. Okay? If anybody's interested in that, they can come and talk to me afterwards. But we're going to focus on the inside. Okay. So volcanoes and earthquakes. Well, the other things that we see are magnetic field. So anybody used a compass or been on, or know what a compass is, been on a plane, have a GPS, well, I guess the GPS doesn't really use a compass, but yeah, we've all used compasses, or we know what it's all about, right? It tells us where the North Pole is. It tells us which direction is north. And the reason why we can use a compass is because we have a magnetic field that is produced in the center of the planet in the molten part of the iron core. And on the very inside of that core is a solid iron. Okay? Now, it looks very different from a magnet that you might find on your refrigerator, but the shape of it looks very similar. Okay? It has a north and a south pole. We'll get to that in a little bit. Okay? But all these cool observations that we see here on the surface, okay, that we've come to just take for granted, right? Well, the Earth hasn't always looked this way. Right? Actually, in fact, the Earth was very different some 4.5+ billion years ago. Okay? So this is an artist's impression of what an early Earth would have looked like right before the moon forming impact, or right as the moon forming impact. So this is a growing Earth. Notice it's got a bunch of spots all over it. Those are impact craters. Okay? So we're thought that the planet and all the planets were born this way, okay? Built up from smaller objects, like meteorites, until they got very, very large to have their own gravitational pull so that they could attract other objects like this one, which is probably about the size of Mars, okay, hitting or impacting this proto-Earth. Okay? So this kind of impact would have been very, very hot, okay, very, very violent. Okay? So you would have been extremely hot. The planet was likely mostly molten, or at least the rocky part of it is. Okay? And it would have looked nothing like it does today. Okay? So the question then becomes, how do we go from this really hot, molten, pockmarked surface to something that looks more like this? Now this is just a cartoon too. It's much more complicated than this. But we've got continents and oceans, right? Inside, so we have the crust, that's where we live, that's where the oceans are. But beneath that, we have this vast region called the mantle. This is the rocky part of the planet, and it's solid. Okay? Pretty much 99.999% of it is solid. Okay? It's not molten, even though our lavas and our magmas come from there. Okay? It's mostly solid. Beneath that, then, we have that core where the magnetic field is made. This is iron, this is basically rock in this green, and then on the top here is the crust. So we call this layering. The word is called differentiation. So it's been the layers in the planet have been stratified that way because or it went from this to looking something like this. So fully molten to basically mostly solid, except for this region here where in the core where the magnetic field is being made. Okay, so how does that happen? So a couple of things that we know about the Earth. We know its mass. We know how its extent and how big it is, what its volume is. Okay? But it's often, since we live here on the surface, we live here on top of the crust, it's hard to kind of imagine the size, right? How deep it is and how big it actually is. Okay? But what I want to get to you is that this mantle part, okay, is about 2/3 of the mass of the planet, and it's more than 80% of the volume. Okay, and this is where most of my research is done. So it's in the vast majority of the planet is this solid rocky part. And this is where most of the stuff is happening that is causing those earthquakes and is causing those volcanoes that we see, right, that we observe or we feel. Okay? The core is basically the remainder of it. And the crust doesn't even come up on this list in terms of the amount of mass or the amount of volume. It's such a small fraction of it. It's just the very, 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 very thin layer, even though we've got really large mountains and so forth. In comparison to the rest of the volume, to the rest of the mass of the planet, it's very insignificant. So how do we know this about the Earth? I can show these pictures, but how do we really know what's going on? Okay? So there are 4 subdisciplines that study the inside of the planet. Okay? So we have seismology. So this is the study of sound waves that travel through the planet. And those sound waves are generally produced by earthquakes. Okay, so we have an earthquake here, and those sound waves travel through the planet and picked up by a seismometer. Okay? Or if you don't have a seismometer and you've ever felt an earthquake, anybody actually ever felt an earthquake? Where'd you feel your earthquake?
Nicaragua.
Ooh, could have been a big one.
It was pretty big.
Yeah, that's not one we normally hear. Well, some of the other places where some other earthquakes have been felt. Japan. Oh, also potential for a very large one. Yes.
Hawaii.
Yeah. Okay. Good. Did you see the volcanoes there too?
Also India.
Ooh. Not So these are actually really quite active places. Anybody feel we had a small earthquake here in Connecticut not too long ago? You remember feeling it? Okay, I actually didn't feel it, but it did register. It did register, and if you were close enough, you would have been able to see it. I'm sorry? No? Okay. I didn't hear it. Okay, so so these earthquakes, so we found that, so there's Japan, Nicaragua, here in Connecticut, and I forget what India, right. So except for the one here in Connecticut, those other ones, oh, and there was one in Hawaii too. So except for the Hawaii one and the one in Connecticut, those earthquakes were produced because you basically had two plates kind of jamming into each other, and then one has got to go underneath, okay? So these are subduction-related kinds of earthquakes. Okay, these tend to make the really large earthquakes. Okay. Anyway, so we have earthquakes, and those sound waves are going to travel through the planet. So that's one way we can tell about the Earth. Okay? The other thing we can tell is like, all right, well, we have samples of what's coming out of the Earth, right? We have lavas. Okay. Actually, I have here. So this, I'm proud to say I actually picked up myself. I'm not a field geologist. I work in a lab, so often when people say, oh, you're a geologist, you can identify any rock. Well, I'm not that kind of geologist. But I did go out into the field, and I did pick this one up. So I found this one in Kilburn Hole, which is a crater. It's a volcanic crater in New Mexico, southern New Mexico, very near the Mexican border. And what it is, so the black part of it is actually a basalt. Okay, is that word familiar to anyone? Basalt? Yeah, do you know why it's familiar? Or why is it familiar to you?
It's a type of volcanic rock.
Yeah. And where do you normally find basalt? Do you know?
At the base of a volcano.
The base of a volcano, okay. Hawaii is a good place to find basalt. Things basically where you come from some depth, some pretty deep. But what you'll notice about this basalt is it's black. Okay, it's a very dark color, and this is typical of a basalt. Now, that's not the cool part. Okay, the cool part, what makes this particular rock interesting, is that there's all these little green and brown minerals that are kind of interspersed within this basalt. Okay, and these are actually pieces of the mantle that came from about 150 kilometers depth. 150 kilometers. Anybody know how far that is in miles? Roughly, it's about 100 miles. So it's like you driving here to New York City-ish, kind of, okay? That's how, and instead of going from here to New York City, imagine drilling down that far, okay? So it's really far, okay? And the thing is, though, this wasn't drilled, okay? This came up with a volcanic eruption, okay? And instead of looking like everything else, which is the black basalt that it would have come up as most of the rock would have, this came up intact. Okay? And it's thought that this would actually pull up from the sides of the magma chamber. Okay? And it came up so quickly that even though it was hot, it didn't melt because it happened so quickly. Okay? And so now we have a piece of the mantle that came from 150 kilometers depth. Okay? Which is kind of cool, right? Now, does anybody know how deep we can actually drill into the planet, or how far people have drilled into the planet? You have any ideas?
So deep.
Yeah, how deep?
Let's say 1 million kilometers.
1 million kilometers. Whoa, that'd be really deep. Yeah, no, the planet's not quite that deep. Any other? A few kilometers, right. Yeah. So like, if we want to just kind of round, about 10 kilometers is the deepest that any of our drills have ever gone. Okay? And what happens after that? How come haven't been able to drill deeper? No. Oh. Do you have a question? Do you want to? How come we haven't drilled any deeper? We can't find it. Yeah, it turns out that our drill bits actually can't handle the heat at those depths, and they just can't handle the rock. They're not strong enough. Okay, so the drill bits break, and then we're stuck. Okay, so we can drill pretty deep, and there are efforts to do this, but not nearly as deep as we can just naturally that come up sometimes. Question here. Oh, you can make a diamond dip, and they have, and it's still not hard enough. And in fact, okay, so I actually use diamonds in my research. Okay, and what do we know about diamonds, right? What do you hear about diamonds? Hardest material. Diamonds are forever, right? I can easily say, and I've lost track counting, but I've easily at least broken at least 100 diamonds in the course of my time doing what I do. So unfortunately, even a diamond-tipped drill bit hasn't been able to go deeper than that.
How about obsidian?
Say again?
Obsidian?
No, actually, obsidian is even weaker. Yeah, obsidian is a glass. It is actually a glass. It's a very dark glass, and it would be much weaker than the diamond. Yes.
So if you like drill too deep, you would either because like in the earth there's like it goes like when you get more into like near the middle, it starts to get like really hot.
That's right. It becomes really, really hot, and that's why they can't. When things get hot, when these metal or even diamond drill bits get hot, they get weak, and so they're unable to drill any further. And remember this. So actually, did I even mention that? How deep is it? How deep is it to get to the core? From the surface down to the core is about 6,400 kilometers. Okay, which is really deep. And if we can only go about 10 kilometers, we're nowhere near the mantle and the core, for that matter. We're so far away. Okay, so anyway, so we have seismology, we have samples from the Earth. We also have samples of meteorites, which is what we think the planet was made up of. We have models that look at how material moves, so this is geodynamics. And then finally, we have mineral physics. So mineral physics is my part of this puzzle in trying to understand what's going on inside the planet. Okay? All right, so let's go on. So that's mineral physics. All right. So here is a map of recent earthquakes and volcanic eruptions. Okay, so in the little black triangles are some volcanoes, and then in red are earthquakes. So what do you notice about this map? Yes?
It's showing in the places that have had earthquakes and volcanoes in the past years.
Yeah, so what about those? Where are they located? They're located in different. They're located all over, right? All over different countries. Yeah. Hot climates. What about up here? Is that hot? We got Alaska here. Somebody's taking an earth science class. We got the Ring of Fire, right? Okay, so around here, sort of just going around the Pacific Ocean is what's been called the Ring of Fire. And it's called the Ring of Fire is because, one, many volcanoes are around it, right? And also earthquakes. So for the most part, wherever you see a volcano, you also see earthquakes. Okay? With a few exceptions, right, like here. But for the most part, if there are volcanoes there, you also get earthquakes. Right? Question? Okay, yeah, so there are different kinds of earthquakes and there are different kinds of volcanoes. Absolutely. So in the where you have subduction, so where you have two plates coming together and one sinks underneath, you can get very large earthquakes. This is what happens in Japan, for instance. Okay? Now Japan also, so Japan here, right? Here is Japan. Lots of earthquakes and lots of volcanoes. Okay, so what happens when you have the oceanic plate, so the Pacific Ocean plate here going underneath the Asian continent, okay? What ends up happening is this doesn't like it, right? I mean, there's going to be some friction here. The friction is part of what is causing the earthquakes. Okay. Now, the other thing that's causing the volcanoes, though, is that as you get these plates dipping down or subducting underneath the other one, it's also dragging other stuff with it. Okay. After all, it's part of the ocean plate. So other things that it's dragging down there, well, okay, so the oceans are full of water, right? So what do you think might be down on the ocean floor? Or the kinds of rocks that are down on the ocean floor? Yes. Sand, okay. Basalt, yes. There are lots of underwater volcanoes. Yep. Right here? Rocks? Yeah, lots of rocks. What about some what happens when crabs die or lobsters or some sea life, and they have hard shells, okay, right? So those hard shells are actually made out of, there's some carbon in there, some water. Anyway, so we get these hydrated and even carbonated kinds of rocks and material down there at the bottom of the ocean, and some of this stuff gets subducted as the plate goes down with it. And this provides then things like water into the mantle. And what happens when we put things like water into the mantle, it actually the minerals that hold this water are weaker than the minerals that don't have the water or the carbon in them. Okay? And by weaker, what that means then is that the temperature that it takes to melt it is much lower. Okay? So it doesn't take as much heat in order to melt these hydrated rocks. And so that melted rock becomes the lavas that feed those volcanoes. Okay? So where you have subduction, okay, like here in Japan, here near Alaska, here along the Central America and down the coast of the South America, you have lots of volcanoes, lots of earthquakes. Okay. In the middle here, so here we have Hawaii. This is where I grew up, right? Lots of volcanoes, and even an earthquake that was felt. And there are some earthquakes there, but mostly known for its volcanoes. These volcanoes, though, aren't generated the same way. Okay? These volcanoes have basalt. Okay? And those magmas that are feeding those magma chambers and then what comes out as lava are thought to come from really deep inside the planet, perhaps even thousands of kilometers. Okay? Rather than these ones here that come out at subduction zones, those ones come from more shallower depths. Okay? So like 100 kilometers instead of thousands of kilometers. Okay, so let's look at these earthquakes. I'm going to need a volunteer. Okay, right here, perfect, right in the front. Okay, so earthquakes provide sound waves, okay, that go through the planet. Okay, so we're gonna mimic that with a slinky here, right? I'm going to have you hold one end. Okay. Now, why don't we put it on the table here? So you stand on one end there, and okay, perfect. You just stay there. Okay, so hopefully you can mostly see this. All right, so there are three different kinds of waves in the planet, but the two most important for the interior of the Earth, interior of any kind of body, are called P waves and S waves. So a P wave is a compressional wave or a pressure wave. That's what the P stands for. Okay, so I'm going to give a pressure wave here, and that's going to look like this. Okay, so you see as the slinky is moving back and forth, okay, the wave is going towards, what's your name?
Juliet.
It's going towards Juliet, and then it's bouncing back and coming towards me. Okay, and how fast it's moving back and forth is dependent on how fast I'm moving my hand. Okay, but you can do this, and you'll see this sort of packet going back and forth. This is a P wave. This is the same way that you're hearing my voice right now. Okay, the air is moving and it's vibrating your eardrums. Okay, and it's moving like this. And so depending on how I'm talking, it'll move your eardrum either really quickly or more slowly, and then that is being translated as sound into your brain. Okay? So those are P waves. Okay? Now P waves move the fastest in the Earth. Okay? This moves really fast. Now the other kind of wave important for the inside of the Earth are called S waves or shear waves. And shear waves, so you can step back. Okay, so shear waves move like this. Okay, so so we can have a wave that goes up and down. We can have a wave that goes side to side, which may be a little bit easier to see if you were looking down this way. Okay, and these waves move slower than P waves. Okay, but they move sort of the motion this way is okay. So when we propagate, when we move a P wave, right, we're going back and forth, right? But when we're moving a shear wave, okay, it's sort of cutting the air in this case. Okay. Thank you, Juliet. Now, what's special about the differences in these waves is how they can travel through material. Okay, so compressional waves, P waves, can travel through air, right? Like how you're hearing me. It can travel through things that are solid, and it can travel through things that are liquid. Has no problems, right? You can talk underwater, and you can hear it. It may sound distorted, but you can still hear it. Now, this is true of P waves. S waves, though, are unable to travel through liquid, and this difference makes it useful to tell what's going on inside the planet. Okay? All right, so for instance, now this is a busy, busy figure. Okay, but if we have an earthquake here, and this one here says earthquake epicenter at Northridge, California. Okay, so there's a big earthquake in Northridge, California in 1994, I believe, 1994. And lots of damage and so forth. Actually, that kind of earthquake was not produced like the ones we talked about today. That was actually produced because of friction this way, a strike-slip type of friction. Okay. Anyway, irregardless of how it was formed, that earthquake is going to send waves through the planet. And if we have layers in the planet, okay, how the wave travels through them is going to, how fast they travel through them is going to change depending on what it's going through. Right? So when I'm talking underwater, my voice sounds differently than when I'm talking in air. And that's because the speed at which my voice is traveling is different between the two. Okay? So I mentioned that this part here, this outer core, was liquid, which means your S waves can't travel through it, but your P waves can. Okay? So as we have a wave, and these are the paths that a wave might follow, okay, they will start to turn around depending on the rock that it's going through. And then it'll bounce off on these surfaces where they're really different, where you have rock versus metal. Okay? And so you'll get these changes in its path, okay, depending on what it's going through. Okay, so if we can, say with experiments, be able to tell how fast a wave travels through a material, we can then tell you what kind of rock and what kind of metal this has to be. Okay? And so you can put together models of how the density and the velocities change as you go deeper down into the planet. So you'll see here that all these little steps here as we change in density, so that the planet gets denser as we go down deeper. And then there's this big step from here on the mantle rocky side to the core side. You get almost a factor of 2 increase in the density. And why is that? It's because we're going from a rock to a metal. We're going to iron, which is very dense, especially at those pressures and temperatures. You had a quick question?
Yeah, I just wondering about volcanoes.
Yep.
What causes them? What causes them to volcano?
Yep. Yeah, so the volcano has, the lava that comes out of the volcano had to be hot enough to melt the rock. Now, if it's hot enough to melt the lava, then why doesn't everything else melt too, right? So there has to be a change, a different chemistry. And that, so to lower the temperature that something has to melt at, we can add water, right? That's one of the ways that can be done. And so then those rocks that have a little bit of water in them will melt at a lower temperature. And so we could have melt there, which is where the lava and the magma are from, and everything else would remain solid. Because after all, we don't have a lot of melt presently today. Yes? That's because there's a lot of subduction going on and a lot of there's just a lot of tectonic activity, right? So where we had volcanoes, we also had earthquakes. The opposite isn't true. I mean, we have earthquakes, many places where there are earthquakes and there aren't any volcanoes. And that's because, like in California, at least for this Northridge earthquake that was shown on the earlier, that was caused because of friction this way. So just sliding, okay? So just sliding that's next to each other rather than dipping underneath each other. So there wasn't a chance for water to get into the planet, but we weren't forming any volcanoes that way there. Okay, there are mountain ranges, okay, but those are produced because of all this grinding that the rocks are doing. Okay, so let's move on as we're going through. So the other thing that these seismic waves can tell us about is how these subducting plates, so here in blue here, are these subducting plates. So these are like in Japan, where you have one plate full of water going down underneath the continental plate. Okay, so we can image those plates, and that's what's shown in these blue parts here. Okay, so you have subduction here, subduction all along the South America, in Japan, here just above New Zealand, where you have these subduction going on. Okay, so let's look at those volcanic rocks. Okay, so this is similar to the rock that I showed earlier. So we have the basalt, and then you've got this greenish part here that's full of olivine, which is one of the main minerals, or the most abundant mineral in the upper part of the mantle. Okay, this is what basalt looks like, molten, flowing in Hawaii. Okay, so when it's still molten and very hot, you see that it's still yellow and red and orange. As it cools, it'll form a black crust, okay, which is the same thing as shown here. Okay. So we have these very dark rocks, basalt. Okay. Now on the other side of the spectrum, the other kinds of volcanism that we see here on the planet are things like granite, right? Or what maybe some of your countertops are made of in your kitchens. So granite, which in this case can come in many, many colors, but is very white here. And actually, Mount Rushmore is been carved out of granite. Okay. Here's another granite here, so it's a little pinker. Okay. Now these two rocks are quite different. They're very different. Okay. This kind of granite would come out of, or these kind of lighter rocks would tend to come out of volcanism that is produced near subduction. Okay. whereas these basalts are produced much deeper. Okay, so this is the kind of lava that you'll find in Hawaii, for instance. Now, so we have very dark rocks, we have lighter colored rocks. Okay? Well, what about meteorites? So I said meteorites are what are the building blocks for the Earth. Okay, these are the little things that are accreted together in these big impacts that then form the planet. Okay, so here's just a few meteorites. These have been collected. This is an iron meteorite, and as like the name would suggest, it's basically all iron, iron and nickel. There might be a few other elements like carbon or sulfur or silicon or maybe even a little bit of oxygen, but it's basically all iron. Okay? Then we have meteorites that are more stony, okay? And then we have meteorites that are a mix of iron and some minerals. Okay, so you can see like the green and orange here too. Okay. So what's different? What's the first thing that you look at this that's different as compared to the granite and the basalts that we find on the surface of the Earth? What's the main difference that you see between these? Any? Sure.
They're more like kind of blackish.
They're more kind of blackish. They are. They tend to be dark. They also tend to be shinier, maybe. Yeah, shiny. They got a lot of metal in them. They have a lot of iron in them in comparison to the rocks that we find here at the surface of the Earth. Okay, so this is puzzling, right? Like you find a meteorite. If you ever has sort of meteorites are mostly found like in places where it's really obvious, like Antarctica or in the middle of a desert. So if you see a black rock sitting on some ice or in the middle of a desert, it'll be like, what is this thing doing here? Okay? And so that's like the first clue. And then you pick it up and it's really heavy. Okay? It's really heavy. It's because there's a lot of iron in those things. Okay? And that's fine because even though we think this is what makes up the Earth, okay, we had to make a core. Right? The core part of the planet is made up mostly of iron. And so where did the iron come from? Well, it had to come from the meteorites. Okay? And its density, its heaviness, allowed it to sink under gravity to the center of the planet. Okay? Okay. So we have some composition. We have the waves that travel through the planet. Now let's go to my part of it, the mineral physics part of it. How do we combine those things and take it further? Okay? So we have to run some experiments. Okay, so I said earlier that I use diamonds, and I do. And you might think, okay, I can produce all the pressures and all the temperatures inside of our planet. How big do you think my diamonds are? These massive diamonds. The diamonds themselves are actually pretty small. Okay, so about quarter carat, maybe quarter to a third carat. Okay, so think of like a modest engagement ring size. Okay, and if you can see from the back, which you probably can't, there are two of them, one on this side, one on this side. Okay. And so you can see them there from the side. And so these are small diamonds. They're small. They're only a couple millimeters in height. And they're shaped like a brilliant cut diamond, more or less. But what we've done is cut off the tip here, shave down the tip, so there's a flat surface between the tips of those diamonds. Okay? And then we can put a sample, a rock, a piece of metal, water, whatever you want, okay, in between those two diamonds, and then we can press them together. Okay? Because diamonds are hard, they're strong, and they're transparent to many forms of light, we can look at our sample while it is under high pressures. Okay? So, for instance, so I take this, I put my sample in between, I close it up, okay? And if I were to just now stand on this diamond cell, the weight, my force, due to just my mass, my weight, okay, would provide about 10 gigapascals of pressure onto my sample. Now 10 gigapascals, I don't expect anyone to really fathom how much that is, but it's about, or it's 100,000 times the pressure that your ears are feeling right now. Okay? And it would correspond to roughly about 300 kilometers depth. Okay? So deeper than any rocks that we have samples of. Okay? Just with my body weight, I can produce that. Okay. You said I could do all the pressures in the Earth, right? Okay, so let's look at this another way. So here's an elephant. Elephant, big, right? Largest living land animal. Imagine putting this elephant in a stiletto heel. Okay? Hard to imagine, yes. Okay, fine. Now, if I put this elephant in a stiletto heel, so a stiletto heel, the area of the heel part is about this big, okay, roughly. Okay? And if anybody's ever had their foot stepped on, irregardless if it's a stiletto heel or not, you know that it hurts your toes, right? It's a lot of pressure. It's a lot of pressure on your feet. So this amount of mass and this amount of area, or this amount of force per area, which is what pressure is, would only correspond about half a gigapascal, half a GPa. Half a GPa, that's about 5,000 times the pressure that you're feeling on your ears right now. Okay? So it's less than what I can do in my diamond cell by me just standing on it. So it would actually take about 700 of these elephants stacked on top of each other in a stiletto heel to produce the kinds of pressures that I can in the diamond cell, or to produce all the pressures in the Earth. Okay? And that's because the area of that diamond that I'm looking at is about the size of my hair, the thickness of my hair. That's how small it is. Okay. I have these diamonds. They're not actually real diamonds. But just to show, right? You put your sample in between there, and then you can press it. Question?
So, say if that small thing is indestructible, and you put an elephant on top, how much pressure would that be?
So if I put an elephant on top of this, let's see. So I'm about, how did I do it? So an elephant is about 5,000 kilograms. I'm roughly, and I'm rounding these numbers, 50 kilograms. Okay? So 5,000 versus 50, right? So we have a factor of 100 there, difference. Okay, so if I put one elephant on my diamond cell and let it do its thing, then it would produce 1,000 gigapascal, which is much higher pressures than in the Earth. So in the Earth, we have about 350 gigapascals. Yeah. So if I had an elephant in my lab, I could put him on my diamond cell. It'd probably be really messy, but you could do that. Yeah, good question. Okay. So that gives us pressure, but how do we get the temperatures? After all, the Earth is hot inside. Okay, the highest temperatures probably in the core of the planet is probably something of upwards of 6,000 Kelvin. Okay, so it's really hot. So what we can do is we can actually shine a laser onto our sample sitting between those two diamonds and heat it up. And we can heat it up to thousands of degrees. So temperature is not an issue. Okay. I'm gonna so since I've already given you a little bit of flavor of what these pressures mean, I want to go a little bit further than that because just to kind of catch you guys up. So our ears are very sensitive to pressure. Okay, when if you've gone up into an airplane, right, you have to clear your ears because your ears can feel that pressure change as you've gone up into the atmosphere. The pressure actually decreases when you're at elevation. Even if you just drive up to a mountain, if anyone goes skiing or so forth, they drive up to the mountain, you'll have to change, you have to click your ears because the pressure on your ears have changed. Or when you dive down deep into the deep end of the pool, you can feel the pressure increase on your ears. Okay, so our ears are quite sensitive. Okay, so the pressure, around 15 pounds per square inch. For those of you who think in PSI, 1 atmosphere is about 1 bar. Okay? That's the pressure we're feeling here since we're basically at sea level. Okay? But then if we just dive down to the deep part of the pool, okay, so we're not very deep into the pool, the pressure has already increased by 30%. And why has it increased by 30%? Why has the pressure increased when we go down into the deep end of the pool? Because water is denser than air. Right. So all that mass of that water is now pushing up against your ears. Okay? And water is definitely denser than air. Okay? So it doesn't take very much to increase the pressure. Now, rock is also more dense than water, and iron is even denser still. So that's why as we go deep down into the planet, the pressures get higher and higher. Now, if we were to go down to the deepest parts of the ocean, so in the Pacific, the bottom of the Mariana Trench, which is at a depth of about 10 kilometers, okay, that corresponds to about 1,000 times the pressure you're feeling on your ears. And then if we could go all the way to the center of the planet, it's 3.6 million times the pressure on your ears. Okay, so these are incredible pressures. So this is how the pressures increase. So basically it's 0, and then we increase in pressure, and we increase in temperature. Really, really hot. Okay, so when it's hot, though, how do you lose this heat? How do we transport this heat? That becomes the next part of this puzzle. How do we transport this heat? So we're all very familiar with how we actually can transport this heat. Okay, and in the Earth, in the deep part of the Earth, the main form of heat transport is through convection. And what that means, and what that's shown here, is hot stuff rises because it expands. And then as it rises, it can cool. But as it cools, it contracts and becomes more dense. So as it becomes more dense, then it drops down. But when it drops down, it hits something that's hot, and it expands, and therefore gets less dense and rises. But it cools, and then densifies, and then drops down. And so you have this cycle, this convection cycle. Okay, we can see this in a teapot. All right. Oh, and I even had something going on here that I wasn't paying attention to. Oh. Unfortunately, I think it's not hot enough. Anyway, maybe for those who are interested, we can look at it later. This happens in water. This happens also in air. This is what you might feel it as we're in winter time here, right? Heat rises, and cold air, hot air rises, and cold air drops, sinks. Okay. So this kind of mechanism is also going on in the Earth, but at a much larger scale. Okay. This is how we get mixing of the mantle, and this is actually how we get mixing in the core. Okay. So let's look here in the mantle. So hot things are rising, okay? But then cold things, like oceanic slabs that are, say, sinking underneath Japan, for instance, are sinking. But then they come back down here, and it's hot. It's hotter down here than it is up there, and so they might rise again. Okay, and so you get this motion, this convective motion, that is mixing up the inside of the planet. And when it's mixing up the inside of the planet, well, that's got to do stuff to the top, right? It's got to affect the surface. And in fact, it does. So here's a map of all of the major plates that are part of this plate tectonics. Okay? So we have this large Pacific plate here, where the ring of fire is around. Right? And the arrows here show the motion of where those plates are going. And this motion, so on this side of the plate, it's actually going down. But on this side of the plate here, it's actually spreading. Okay? So new land is formed here with volcanism, but it's being destroyed or being subducted on the other side. So you have parts where you have magma would be coming up on this side, and then plates are going down on this side, like we saw in the other figure. So we're seeing an expression of all these, of the plate motion here is occurring because of the convective motions underneath. Okay? And that's what's giving us all of our volcanoes and our earthquakes. And they line up very nicely on those plate boundaries. So if you missed that, I'll show it again. So we have the plate boundaries here, and I tried to line them up with the earthquakes. And you can basically draw the same map just by drawing the outlines of those earthquakes. So I'm going to end and say, like, this is what we've been able to do. We've been able to take seismology, mineral physics, petrology and geochemistry, as well as geodynamics, or this convective motion, and describe what's going on the inside to then tell us or inform us about what is on the outside. And so I'll end there, and I'll take any questions. Yes? Uh-huh. Oh, those are very comparatively quite shallow. Much tens of meters. I mean, not deep at all. Yeah, they're
actually working really well.
Oh, is it? Yeah, kind of. I think I should have turned it up a little higher. So what we show on the video here, we have some corn syrup that I'm heating from the bottom. And so on the bottom here is hot, and on the top is relatively cold. And so you'll see little bubbles that are rising, right? Hopefully you can see it. If I had been paying attention, I would have. It may be too warm altogether, but if you do this properly, what you'll be able to see is you'll start to see these plumes of hot material coming up, like we think is going on in the mantle. Okay, so we can model that with some corn syrup. Yeah. Question here.
You showed that certain plates are pulling apart versus some of the plates are coming together. Where new land is being created because they're pulled apart, is there evidence that's being noticed of new lands coming up in those?
Oh yeah, those are all underwater volcanoes. They're called midocean ridges, and let's see if I can. So these volcanoes here are the ones you can see on the surface. But where all these red parts are, where they're earthquakes, that's a midocean ridge that is defined by volcanism. Yeah, but deep under the water, so you don't see it. But they've taken samples and so forth. I mean, does anybody know how fast this is happening? That's something we haven't talked about. Like how fast things are moving on the surface. Do you know?
I know that New York and London moves apart 1 inch per 100 years.
That's about right. Yeah, that's about right. Okay, so we're talking about millimeters to centimeters, depending on where you are on the planet. Millimeters to centimeters per year. Okay, it's about as fast as your fingernails grow. Okay, that these plates are spreading apart. Okay, that the plates are spreading apart and then being taken up by their subduction on the other side. So yeah, everyone's looking at their fingernails like, I cut my fingernails about once a week. Maybe my nails grow a little faster than others, but that's how fast these things move. Okay, so the convection underneath is moving at those scales. Okay, so even though it seems rather slow, it's something that we can measure. And obviously, we can feel for those of you who felt earthquakes. Yes?
So is it true that California is sinking?
No. I don't know what you mean by that. California is moving laterally, so there's so lots of earthquakes, along the west coast. Okay, that's because the Pacific plate is moving with respect to the North American plate. So they are moving like this, but not underneath. Yeah. So, yes.
Can you describe the mechanism for the hot spot in Hawaii? Because when we were there, they were always telling us there's a hot spot, but they could never explain what is the physical mechanism behind it, since you were saying that it probably isn't the water-filled rocks underneath.
Right. So if this one would have worked like I wanted it to, so we think that the hot spot that is feeding the Hawaii volcanoes actually comes down from the core mantle boundary, so almost 3,000 kilometers depth. Okay, where it's really hot. Is it
going down?
Oh, here we go.
It's going down.
Is it going down?
It's going down. You can see the bubbles going down here.
Oh yeah, here.
Coming up.
That's right. So you have bubbles coming up here, that's hot, and then you have other stuff that's coming down. So this is stuff that already went to the top, got cold, and came down. So imagine now if Hawaii as a hot spot, so that material, okay, would be coming from this depth. Now, it wouldn't be molten at this. It would just be hotter than everything else. So it would be buoyant, but not molten. It doesn't actually melt till it gets to the surface. But it's rising because it's really hot down near the core. So like 4,000 degrees. And by the time, but it's solid, yeah.
And
Yeah,
it's
just
stable, like in that one location?
That's what it appears to be. Because, yeah,
Why is it stable?
Why is it stable? I mean, this is a hugely. I mean, this is under active.
But the plate
Yeah.
moves across.
But the plate moves across. So I don't have a good map, but for those of you who don't know, so Hawaii has many, many islands. There are 132 islands that make up the Hawaiian chain. And where the active volcanism is at the most southeastern part of it. So here, but it stretches up past here at sort of this angle. And then there's actually a kink in it that goes a little more north. And so that kink, and then they can date how, when these things would have occurred. That kink then represents probably a change in the entire plate motion. So the plate is moving over this, what appears to be fixed hotspot. And I mean, that's the best sort of hypothesis at this point, given the data that we, and observations.
The islands move past it? So that's why you have a chain of islands?
That's why you have a change of islands, yeah.
Moves, and then a new island pops up.
A new island pops up.
They keep moving.
Yeah, so the plate moves, and then this magma is just coming up. And as the plate moves, it just pops up new islands. Yes, another question.
I was wondering, so I've seen on some tectonic maps that you can see in Africa, if there's like a line going through it. So is that because the plate is splitting, and if so?
Oh, you mean the here? Hold on. Right here? Yes.
And so the plates ever merge together again?
All the time. Actually, and so there are these things that are called supercontinents, and the last supercontinent was called Pangaea, and about 200 million years ago, you can actually kind of fit the pieces together. So like this part of Africa here would have kind of fit South America here, and this part here would have fit over here, this part here onto Europe. And all the continents you can imagine now were part of one large supercontinent. That broke up about 200 million years ago with this ridge, which is called the Mid-Atlantic Ridge. So this ridge here is spreading those continents apart. So that is happening. Now here in this ridge system too, that appears to be happening too. You have some ridge action going on here, so some splitting. Now, again, this takes a really long time, but it is, at least there's evidence for several of these supercontinents over the last 1 billion to 2 billion years. Yes?
So we know at the rate that they're separating, we can calculate when they will touch on the other side, right?
Exactly. Yeah. And then we can compare that to the rate that is being currently measured today. And it's pretty constant, at least for the last 200 million years, yeah. Mm-hmm.
Yeah, so there have been a lot of earthquakes caused by fracking in Oklahoma.
Yes.
Oh. That water eventually leads to a volcano.
Oh, that's a good question. Okay, so for those of you, so let's just background. So the question was on earthquakes that have been induced by fracking in Oklahoma. So Oklahoma, we all know California's got lots of earthquakes, right? That's pretty common. Actually, Oklahoma today has more earthquakes than California does. Okay, which this was not true 10 years ago. Okay, and the thought is that so when you frack, so fracking is a kind of way that you can extract natural gas or oil from the rocks. Okay, and you use water to basically fracture the rocks, okay, and pull out that natural gas. They use the water to pull out the natural gas, but then this water ends up being kind of yucky and dirty, so that afterwards, after they have this water, it's not a good idea to then put it into the rivers or lakes because it'll destroy the drinking water. So they put it back into the rock. Okay? This increases the pressure on the rock, okay? Which then, if you're increasing the pressure on something, think of, this is a different kind of pressure, but think of when you're trying to boil a pot of water on your stove, right? And you put a lid on top of it. And as it starts to boil, right, that gas pressure of the water being vaporized as it's being boiled starts to pop up. Okay? So this kind of pressure, a different kind of pressure, but this kind of pressure is going to stress the rock. Okay? And it's the stressing that's causing the earthquakes. Now, his question now was, will that water then affect, could that water then make the rocks melt and then produce volcanoes? So you still would need the rock to be hot in order to get melting, and it would have to be hot enough for that, for any of that water that it would then sort of affect the surrounding rock to sort of join into it and then weaken it so that it would melt. My initial gut would say no, because it's not generally hot in that part, because it's part of a continental rock. Continental rocks on average are colder because they're older, so I don't think it would be hot enough. But I get where you're going in terms of the principles of like adding water to the system. It should lower the melting temperature. It just may not be hot enough still. Yeah.
Has the rate of volcanoes or earthquakes changed within recent history, or is it always been?
In Oklahoma, it has. The kinds of history that we have, in terms of seismometer history, we've got decades worth of data, but we also have written data and written, historical logs on when large earthquakes and so forth have happened over hundreds of years or even thousands of years, when people were taking, if you just read sort of the history. Has it increased or decreased? The seismometers have become more sensitive, so we can measure them. But do we have any reason to believe that as a whole that the Earth is doing something different than it did 1,000 years ago? No, there's no evidence for that. But locally, because of stuff like fracking, yes, in that region there are definitely more earthquakes than there were ever, at least in the recent past. So how are we doing for timing?
We're over.
Okay.
So, if you have questions, stay afterwards. But let's thank Professor Lee for the stimulating.